Yes, wonderful. We're recording now. Thank you. So, we discussed last time the very foundations of what blockchain, or more generally distributed ledger systems are. And we know that they are based on some kind of interactive consistency, or same thing as consensus protocol. These are distributed databases where we keep the whole history of updates. We already know that it relies upon some kind of cryptographic techniques in order to preserve, actually, play the role of a mechanism in this consistency protocol, and preserve consistency and integrity of our distributed database. So today, and maybe next time, depends on how much we can do today, we'll be studying some basic cryptographic primitives which are used in modern distributed ledger systems, so that when we really start studying architectures of, let's say, Bitcoin blockchain, Ethereum blockchain, other distributed ledger systems, then things like, for example, asymmetric cryptography and digital signatures, they would not scare us anymore. And, well, hopefully they're not scaring even now. And we will know precisely how it works and how this can be used. So can you tell me, please, you are from just one specialization or multiple specializations in computer science. So have you had some foundations of cryptography and computer security course in the past?
Yes.
Yes, we had security cryptography course.
Okay.
And there is only one group of students from the security track.
Okay. So of, let's say, 13 of us, by the way, not that many, including myself, who are participating at the moment, what, about a quarter did have it, and others did not?
We're all from the same group and we're all security students.
Ah, okay. Okay, that's great. You are all security students. So in that case, you probably know already what is symmetric cryptography, what is asymmetric cryptography, RSA, perhaps elliptic curves, and so on. All right? Or not
Yes.
quite?
We've
Until
never discussed elliptic curves.
yeah, until elliptic curves, you are right.
Okay. So you know the basics of everything, except possibly elliptic curves, right?
Yeah, we didn't study the theory of them.
I see. So let us, nevertheless, let us do a quick recap in that case. So first of all, symmetric key cryptography. In our blockchain systems, it is not even that much used, because primarily what we need in distributed ledgers is the mechanism for digital signatures, primarily. But in general, let us start with that point. So what is symmetric key cryptography? This is all, well, you know, cryptographic mechanisms which which require a pressure key between the sender and the recipient of a cryptographic message, right? So there must be the same key applied for both encryption and decryption, which must be made available to all parties communicating and involved in this secure exchange. And in that case, same key can be used in order to decrypt a message which was previously encrypted with that key. You no doubt you have seen most commonly used symmetric key cryptographic algorithms. So what are they?
DES, triple DES.
And that's all.
Common.
Well, DS by itself, if you remember, it uses, well, in a classical form, a 56-bit key, and it is considered to be totally and absolutely insecure by today's standards. So DS is really a thing of the past. Triple DS is slightly better and might still be used, but it is not the primary symmetric key method which is used currently. There is another one. Triple DS, okay. AES. All right, so AES. And furthermore, there is a hardware support for AES in all modern processors. Modern Intel chips have built-in AES instructions, which significantly speed up encryption and decryption operations by actually applying all those nonlinear operations with the key shifts, exclusive OR, and so on in one go at the hardware level. And that's why AES is by far the preferred way of doing symmetric key cryptography nowadays. So it is a standard. It is no significant weaknesses have been found in AES. It is a very much standard and recommended way. Okay. Now, what is the major problem with symmetric key cryptography if we're talking about encryption and decryption of messages? It is the weakness of, well, I would say the technical difficulty with the key sharing procedures. You really need to agree with all parties exchanging information with you about that secret or shared key. Secret key cryptography is equivalent to shared key. Shared doesn't mean shared with the whole of the world. It means shared between the participants of the exchange. And by the way, if we talk about, just as a recap, about algorithms like, let's say, DS or AES, what is, let's say, the most important, maybe one of the most important or the most important properties such encryption algorithm must possess? So what is really, really important? Because after all, you know, what you can do, you can generate just a random key and then use exclusive OR, XOR operation in order to encrypt any message, just applying that key. Applying that XOR once again will restore the original message, as you understand, right? Why can't we do that?
Because we need to achieve the avalanche effect, so we will not know anything about the original data when we look at the encrypted ones. So the dispersion will be high to the dispersion.
Well, if, and sometimes it is a plausible assumption, if we have an infinite length key, so imagine that you have generated an infinite, or well, potentially unlimited or very large a random sequence of bits. You apply that sequence of bits using the XOR operation to any inputs. Once a part of the key was used at least once for encrypting one message, it is discarded and never used again. Then you know it is a very feasible way of doing the encryption. It is quite okay. Moreover, such a technique with unlimited length secret key is virtually unbreakable. You can't do any type of cryptanalysis, for example, frequency cryptanalysis, frequency-based, because anyway, whatever relationships you discover for a particular part of the encrypted text will no longer hold for the rest of the text. That will be encrypted with subsequent and totally unrelated bytes of the secret key. So the whole problem occurs if your secret key is not of unlimited length, as usually the case. By the way, in some very much realistic examples, unlimited length secret keys do exist. Have you heard about them?
Yes, it's for, I don't know how they called, diplomatic.
Yes. So basically, that's the standard policy of the US Department of State, for example, that all diplomatic communications are to be encrypted with those completely random infinite length sequences. In that case, the encryption and decryption algorithm is extremely trivial, and the keys are delivered by couriers to all US diplomatic outposts with a strict policy that they should be used only once. And when that happened on a number of occasions, both actually in the United States and in the former Soviet diplomatic encryption of diplomatic communications, that the keys were accidentally reused, and this resulted eventually in decrypting the communications. Because with that very, very simple XOR algorithm, it is very much vulnerable and susceptible to simplest forms of cryptanalysis, for example, to frequency analysis. So once a key is repeated, then the chances are already very high that your communication becomes completely insecure. So for algorithms like DES or AES, where the key size is indeed limited, the major property is nonlinearity. XOR is a linear operation, actually. Whereas reliable, secure cryptographic algorithms would do a combination of, you remember, various shifts of the key and nonlinear operations. For example, they are called S boxes in DES, to make sure that at least there is no linearity property, that, for example, a linear combination, if we can decompose our input into linear combination of other input, then the output is not a similar linear combination, because otherwise it is sufficient to learn very few relationships between the input and the output, and the whole communication becomes decipherable in that case. So, and actually, the very heart, the very essence of the DS algorithm is precisely the design of those nonlinear S boxes. Okay. Do you remember, actually, if you studied DS, what the S boxes are and how they're implemented?
Yeah, but often they're depicted as simple matrices and used this way.
They are matrices, you're absolutely right, but not matrices in such a way as used in linear algebra. In linear algebra, multiplying a matrix by vector is precisely a linear operation. So if you take a matrix and multiply it by vector x1 and vector x2, then by the sum of x1 and x2, then let's say the first result is y1, the second result is y2, and the result of applying this matrix to x1 plus x2 will be precisely y1 plus y2, so that's the linear operation. In Xbox design, they are not really matrices. I would call them simply lookup tables, because they are not used in the sense of matrix by vector multiplication in linear algebra. They are just taken as tables. You remember various bits of input are identified as a row and column number in those lookup tables, and the value of the corresponding bits is extracted from the table. So basically, yes, nonlinear maps are implemented as nonlinear, of course, lookup tables, and those tables are precisely as boxes. All right? Right or wrong? I think right. Okay. Now, can you recall, please, how such a nonlinearity is implemented in AES? That becomes much more interesting.
May you repeat once again, please?
Okay, we just found that the heart of DES encryption algorithm is the mechanism called S-boxes, which provide the essential nonlinearity of mapping from the input to the output, from the plain text to the encrypted text, right? So the nonlinearity of the algorithm is achieved by application of S-boxes. That's in DS. In the more modern AES, how is it done? So again, what is the nonlinearity property of AES? How is it achieved?
It is achieved through various steps of shifts, substitutions, and some other operations that allows to make nonlinear operations and achieve some more efficient dilution and yeah.
Well, first of all, be careful here. Shifts cannot be used as nonlinear operation. It is only just some kind of helper mechanism, but in essence, shift can be viewed as a linear operation. So you can construct even a matrix which multiplication by this matrix will actually achieve the effect of a shift. So don't try to devise your presumably nonlinear symmetric encryption algorithm using shifts. Shifts are only auxiliary mechanisms which are useful in conjunction with others. They are not the foundation of nonlinearity. There is something else which is essentially nonlinear. So taking some byte, actually, if you remember, actually AES is byte-wise. Generally taking a byte, we can get a certain essentially nonlinear operation on that byte. So what is that operation? And only then apply XOR shifts and so on.
The subbytes round is introducing nonlinearity because it is basically the same. So it is an S box by its nature. It substitutes bytes for other bytes.
In AES, there is something. Well, mathematically, you remember when you studied AES, what was the mathematical background and mathematical prerequisite to AES?
The Galois field.
Galois fields, of course. So, what are Galois fields? Galois fields are finite fields with a certain number of elements, which, and that number is always a power over prime, p to the power n. So, for example, p could be equal to 2, and then you can construct a Galois field with, let's say, 256 elements, if you remember, right? How is it constructed? It is constructed as mapping to actually to integers of fields of multiplication operations modular irreducible polynomials in Galois fields. And if there is a multiplication and it is a field, then there is also the inverse operation in Galois fields, and these are essentially nonlinear operations. So nonlinearity is achieved by applying Galois field operations. So these Galois fields are actually as boxes of this. In this as boxes, in AS, Galois field byte inversions. And you see that the operation itself, both actually in this, the structure of S boxes is absolutely open. In AS, the application of Galois field inversion is also a very well known and not that much complex operation actually. It just ensures nonlinearity. So the source of secrecy is in the key, not in the algorithm itself. The algorithm actually is the wider it is known, the better, I can say. Why do you think? By the way, how do you think actually? I'm absolutely sure you have discussed this in cryptography, but nevertheless, what is more secure, to keep your encryption algorithm secret so the adversary doesn't even know how it works, or to make the algorithm itself public and concentrate all your secrecy only in the key?
To make algorithm public, so it will be proven by the community.
So that it can be tested by the community, yes. Whereas for a private algorithm, and what if we keep it private, then we can keep at the same time flaws which are potentially existing in the algorithm and not even learn about them. But what would the adversary do if the encryption algorithm is private? They would try to disassemble it. And whatever code obfuscation techniques are used, nevertheless, they would sooner or later be able to learn the algorithm and, in particular, examine it for vulnerabilities and possibly get some vulnerabilities which you are not even aware of. So this is a kind of standard setup. The American National Institute of Standards, NIST, NIST, explicitly require in cryptographic algorithms that the algorithm itself must be made standard, public, as widely known as possible, and tried and tested by the cryptography community, and the whole secrecy is to be concentrated in the key alone. Okay. And now we are into asymmetric cryptography. So as we said, we have a key dissemination problem. We are not, I presume we are not a US diplomatic institution. So there is no way of how we can carry by couriers an unlimited supply of keys. For the internet community as a whole, secret key, shared key cryptography is not workable because you wouldn't have any ways of sharing the key with your possibly yet unknown counterparty. And without the public key cryptography, all our modern internet technologies, let alone blockchain technologies, would not be feasible. So it was a major achievement when it came to the advent of public key or asymmetric key cryptography. When was it? When was asymmetric key cryptography invented?
If I'm not making a mistake, it was in like 1979 with RSA algorithm or something.
Yes, 1977. It was then patented, and the patent, as a typical American patent, stood for 20 years. Then a certain person actually somehow, because the patented algorithm is publicly available, only you are not allowed to use it for your own purposes. You must license it. But he started disseminating his own software based on the RSA algorithm, and that was actually the precursor of PGP, pretty good privacy, for at that time, of course, it was for email communications. He was sued by RSA Incorporated, but at that time, his shareware implementation of RSA, which was not properly licensed from the company, became already so much popular that it was actually not possible to enforce this lawsuit. And eventually, by the very end of 1990s, very shortly before expiration of the patent, RSA abandoned that patent, and the algorithm became a public domain, which is still, in principle, same algorithm, only with maybe slightly longer keys and other enhancements. It is still in use today. So, because it is so important, and the idea of the RSA, not the mechanism, but the idea, is also used in elliptic curve cryptography. So let us recall, actually, first of all, how public key encryption decryption works in asymmetric key. Let's begin with RSA, and well, in general. So what is the in very essence, actually, the gist of it? So what is the idea? How RSA works? You know, it is a kind of miracle that you can use one key, for example, called, let's say, public key, in order to encrypt a message, and the other key called private key in order to decrypt it, or the way around. But how does it work?
You mean the algorithm, how they're...
We will do a quick recap of the algorithm itself, but I'm interested in the very idea, actually. So what is the essence of, let's say, RSA algorithm? So in principle, not in detail, we'll recap the details very shortly, but in principle, so what is the main idea behind it?
The idea is that using some mathematical problem, I'm not remember exactly what it is, you're able to generate I think I'm missing something. Well, as a result, you have two keys, public and private key. Everybody who has this public key is able to encrypt the message and give it to you, so you're able to decrypt it, and nobody else is able to decrypt it. And everybody else having the public key is able to decrypt the message, you encrypt it with your private key. And this allows you to provide authentication.
But this still doesn't explain that well how mathematically, by which principle, I would say, this could be implemented. And I can tell you the principle is very simple. The principle is, you see, given two numbers, let's say presumably prime numbers, P and Q, it is relatively easy to multiply them and get another number N, let's say, which is a product PQ, right? Even if P and Q are long enough.
Excuse me, I was supposed to see something.
Yes, I'm switching it on. I'm just discussing
Okay.
with you. Of course, you are supposed to see this. It is a discussion at the moment. So, multiplying two numbers, in particular two prime numbers, is relatively easy, even if the numbers are long enough, right? But now imagine the opposite situation. You have a number which you know is a product of two large primes. Factoring it out back into two primes can, in general, it is a unique operation. So when you multiply two numbers, you get a unique result. When you factor this result back into two primes, you again get a unique result, obviously, if it is really a product of two primes. But computationally, this is by far by far more difficult and effectively infeasible operation. There is no way of how you can do it for large enough numbers, apart from currently almost an exhaustive search through the number space. And that would require, even with modern CPUs, the time probably in excess of the whole age of the universe. So although mathematically the operations are both inverse of each other, bijection, computationally, one of them is by far more difficult than the other. And that is the idea. So that's precisely, I would say, the gist of the algorithm. The rest are technical details. We'll recap those technical details in a minute. But in general, it is important to understand that all such, let's say, asymmetric key algorithms are based on the idea that one-way operation is simple. The other way, the opposite way operation, although unique, is so difficult that the adversary wouldn't be able to implement it. So that's how it works. Okay, now let's have a look. Can you see the whiteboard?
Yes.
Okay. So, a recap of the RSA. Why we do it? Because the elliptic curve algorithm is based upon same general principles. One easy operation, well, more or less. The other one difficult, but the mechanics are different. So, RSA. So, first of all, suppose that there are two numbers, P and Q, which are primes. Okay? And we compute, yes, that's easy, PQ, which is the product, N, which is the product of PQ. P and Q by themselves are secret. N is public. It is not the public key by itself. There will be yet another component to it, but it is a very important part of it. Now, we take a certain number, which is called, maybe you have heard this term, which is a Carmichael function, lambda of n, of this n. Carmichael function, what is it? Lambda of n is the minimum m, where m is from 1 to n minus 1, such that for all a, where a, let's say, would be again from 1 to m minus 1, the following property would hold. A to the power of m would be equal to 1 modulo n. Actually, just a second. No, I don't think we need even this constraint here. We do need a constraint on a. Yes, for all a from 1 to m minus 1. That whatever a we take to the power of m and then reduce the result modulo n, the result would be equal to 1. And let us compute the value lambda of this n. First of all, if we compute lambda of a prime, for example, lambda of p, then it is relatively easy to understand what it would be. So for Carmichael function, imagine that instead of n, there is a prime p here. Then whatever number modulo prime is taken, what do we get? It is very easy to see that in this case, m would be equal to p minus 1. It is a consequence of so-called little Fermat theorem. In a similar way, lambda of q equals to q minus 1, and lambda of n, which is pq, again, you can prove it. It could be LCM, least common multiple of p minus 1 times q minus 1. Okay? Okay. So we take this lambda of n. P and Q are sufficiently large primes, but obviously P minus 1 is even, Q minus 1 is also even, and therefore the least common multiple of P minus 1, Q minus 1 is not a product of them. Actually, instead of this least common multiple, you can use a product, but it is unnecessary. So LCM would do. In the original RSA invention of 1977, it was just a product. Nowadays, LCM is used. Furthermore, now take yet another number, which is denoted by E, which is greater than 1 and less than this one lambda of n, and such that the greatest common divisor of E and lambda of n is 1. So they are mutually prime. That is an important thing. We'll use it later. Okay? To that end, can you tell me, please, whether we can use E equal to 2?
No,
No, why not?
because this common multiplier will be even number.
Of course, this is even. So, E is greater than or equal to 3. And actually, you can use E equal to 3. And in the old-fashioned implementations of the RSA algorithm, it was equal to 3. Not anymore. It was found that using a very small number for E can lead to some difficult to explain, obscure, but nevertheless existing weaknesses in the algorithm. It is not, I would say, a principal disadvantage, but it's better to avoid very low numbers. So in most current implementations, E is taken to be 2 to the power 16 plus 1, which is obviously 65,537. Okay. Although the algorithm would work with e equal to 3. Okay. What do we do next? We say that the public key is, what do you think of the public key? Is a pair of two numbers.
E and N?
Yes. Let's do it this way. N, E. Yes. These are public. That's perfectly okay. But not, of course, P or Q. Now, we compute another number. We compute the inverse of E. Let us denote it by D. D is the inverse of E. Again, modular lambda of n, where lambda of n is this one. What is very important in that, first of all, do you think lambda of n is secret or not?
It is a secret.
It is secret, indeed. In general, it is very difficult. N is public, but computing lambda of n from n is extremely difficult. Because otherwise, because what you can do, you can either do it by definition. So basically just increase and increase and increase m. So take different values of a, different values of m, and then try to find a value of m such that for all a, the whole property would hold. And you know what? You will do it for a very long while, because in general, if, for example, although I'm not making any precise statements here, but suppose that, for example, it may or may not be the case, of course, that p minus 1, suppose that wouldn't have any other multiples as, let's say, 2 and p minus 1 over 2, then overall this lambda would still be of order of magnitude of pq equal to n, something like that. So in order to find it out by direct computation, even if you know n, you would really have to perform about n squared tests. So you take different values of m and then all a's in the range from a to m minus 1. So a lot, infeasibly a lot. But if you know the decomposition of n into p and q, then of course you can do it very easily. So as p and q are secret, lambda of n is secret as well. So d is, inverse of e modular lambda of n. So what does it mean? It means that de taken modular lambda of n equals to 1, right? Why do we know that, first of all, such an inverse does exist? And how do we compute it? Given E, compute D, let's say in general greater than 1, such that DE equal to 1 modular lambda of n. How do we know that such D does exist? And how to compute it? Any ideas?
It can be computed using the extended Euler's algorithm because it can be represented as a Diophantine equation.
Not Euler, but Euclid.
Oh, sorry, yeah.
Yes, extended Euclid GCD, extended GCD Euclid algorithm. I presume you have seen it. Basically, what happens is that in general, if we have two numbers, let's say mn, and let's say G is the GCD of mn, then this GCD can be represented as a linear combination of m and n. Sum km plus ln. Let's say m and n are, let's say, natural numbers in this case. Obviously, in this case, k and or l can be negative. So in general, we can say kl are just integers. And in particular, we already required, please look here, in the definition of E, that the GCD of E and lambda of n equals to 1. Therefore, we can write an equation that 1 is equal to k times E plus L times lambda of n. All right? Because E and lambda of n are mutually prime. And this precisely means that our inverse D is the coefficient k, because in this case, k e modulo lambda of n equals to 1. And the coefficients k and l can indeed be computed using the extended GCD algorithm. Once we compute the GCD, we simply keep track, you remember, right, of linear operations which are carried out with our numbers when they decrease and eventually one of them becomes 0. And, well, eventually one of them becomes the GCD, first of all, and then in the next step 0. And that way, we can compute this linear decomposition. If it happened, for example, that the extended GCD algorithm resulted in, from the extended Euclid algorithm, we got k negative, what do? I want my k or my d, which is the same here, which is the inverse of E, to be positive. So what do I do if it is negative?
We can take it modulo lambda n.
Yes, so basically we, if it is negative, then we modify it. We say k plus any numbers of lambda n, which means that k capital E lambda n are subtracted from the other part, and this relation still holds. Yes. So assume that D is positive in this case. Okay. So we got the inverse. And what is the private key then?
The pair of D and E.
No, E is a part of public key. We have already seen that E is included in the public key, E and N. not the public key. So basically the private key is only D. Is only D. So now let's see how the whole story works. Suppose that we have a text to encrypt. So let's say P is a plain text. We interpret it as a number, basically in just in a bit. In convention, we in a bit representation we treat it as a number. Then we compute the encrypted or cipher C, which is simply our plain text to the power of E modulo n. Because E and n are part of the public key, then everyone can do it. Your public key is known to everyone, and actually you know already that the wider it is known, the better. The problem, one of potential problems with public key cryptography would be actually impersonation of the public key owner. So if, for example, you encrypt a message in order to send it to someone, you really need to know that you are using the public key of that intended recipient and not anyone else, because that person in possession of the corresponding private key would be able to decrypt the message. So, okay, using the public key EN10, we can encrypt. Now, decryption, so that's encryption. Decryption will return to P using the following operation. We take C to the power of D, but remember that modulo n, all operations are performed modulo n. But we know that C is P to the power E, so it is P to the power E D modulo n. Not only the result is to be reduced modulo n, but you can also prove that in this case, because ED modulo n, you remember, is 1, they're inverse of each other, you can see that this would be equal to P modulo n. And yes, plain text, our plain text should be less than n. Otherwise, it doesn't work. So we can say that this number P is less than n. And therefore equal to P. So basically, erasing is just power operations. Erasing your plain text to the power E, taking the result modulo n, is the encrypted text. Erasing the result to power D and taking modulo n restores the plain text. So these two operations are very much complementary to each other and completely symmetric. Okay, so that's very simple how it works. The crux of the algorithm is that given E and N, it is impossible to find D by brute force. Because how would it be? Once again, by brute force, it would be from N, you would need to factorize it find P and Q, and then of course you can immediately compute D as the inverse of E modulo LCM of P LCM of, what was it, P minus 1 Q minus 1, not a product but least common multiple, if you know P and Q. So that's elementary. This is extremely hard. So the essence of the algorithm is that even if you know that your number n is a product of 2 primes, finding those 2 primes is an extremely, extremely, extremely difficult operation. Right? Sorry, I have forgotten a comma here. Okay. Have you heard about quantum computing?
Yes.
Slightly.
Not very much.
Well, I would say everyone have heard about it, and no one, almost no one, would know with any kind of detail what, how it works, what it is, and what can we expect from it. But one of the algorithms, which many years ago, I think it was already in 1990s, was shown to work on quantum computers, was efficient factorization of numbers. So if this technology becomes a reality, then this operation of factorizing n into a product of PQ would become easy on quantum computers. And then all our mechanisms, security mechanisms based on current implementations of at least RSA algorithm would become immediately and totally insecure. But that's still a matter of the future. And it may very well be that even that, if that happens, then elliptic curves algorithms, which we are going to discuss now, would still stand. I'm not sure if there are any algorithms on quantum computers which can tackle elliptic curve security. Okay, so now let's probably go and discuss what are the elliptic curves and how a similar algorithm can be implemented. One thing apart from that, one second. So we discussed asymmetric encryption and decryption. Do you remember what are the digital signatures?
So as far as I remember, when you encrypt the message with your private key and anyone can decrypt it using public.
Generally,
Actually,
yes. Generally, yes. So you're right. Why would we do so? You encrypt it. By the way, don't do it in a wrong way if you are really encrypting communications. It is so easy to make a mistake. There was an experiment done on about 100 of US computer science graduates, maybe even they were master level graduates. 70% of them, when asked to use PGP, pretty good privacy asymmetric encryption framework, in order to encrypt email communications, they did it wrong. They encrypted, they were thinking, oh, good, I have my private key, therefore I would encrypt my communication using the private key. It's private after all, right? And then everyone on the internet was able to decrypt them. No, encrypting with a private key, as you correctly pointed out, is for digital signatures. Why would we do that?
To verify,
To
okay, like to verify for someone that, for example, the message, or it's used a lot, for example, for packages that you just take the source code and apply your private key, and they can verify that the sender is actual, like, I don't know how to say, official one.
Well, this simply verifies that, you see, you are a person here, and for this person there is a public key available, all right? So by using the digital signature, you really verify that you are the person who has constructed this public-private key pair. You prove that you also hold a private key. Without revealing the private key. How? Taking some plain text, encrypting this plain text with now private key, right? Returning to the public, to the internet community, a pair of your plain text and encrypted text, all right? And then anyone take this encrypted text, applies your public key. How do we denote public key? The public key was EN. Okay. It applies your EN to that encrypted text, reconstructs the plain text, and compare that they're equal. If from, and this is your digital signature actually. If from this digital signature, by applying your public key, everyone or anyone can hatch out the original plain text message, then this proves that the person who has sent this message is indeed in the possession of the corresponding private key, right? Otherwise, anyone can claim, yes, this public key is mine. It's public after all. Mine, 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 mine. No. Only a person who is in the possession of the corresponding private key can that way demonstrate that they're the legitimate owner of the corresponding public key. And that means the signature, really. This does not solve the problem, although this doesn't solve the problem that, you know, the person who claims it is his public key is indeed Mr. Donald Trump. Mr. Donald Trump claims that, well, someone, we don't see him, say that he is Donald Trump and this is his public key. By using digital signatures, we can say that, yeah, the person who makes this claim does indeed possess this public key because he has a private key and can demonstrate this. And this is called zero knowledge proof because the private key is not revealed. But we perform an operation which undeniably say that, yes, it could only be performed by someone in possession of the private key, right? But this does not, unfortunately, say that the owner of this public key and the private key, as we demonstrated, is indeed Mr. Donald Trump. That's the problem. How would this problem be solved? That really those public and therefore private keys are really attributed to those physical people. So if you are sending an encrypted communications to Mr. Donald Trump, that you are really using a public key which belongs to Mr. Donald Trump and not an imposter. An imposter may still have a private key in his possession, yes, and claim to be the president of the United States. How is this problem solved? Any ideas? Gentlemen, let's remember from computer security, your computer security course. So what do we do in that case?
We need to have a special signature, right?
I would say there is absolutely no way without involving extra tools, extra mechanisms to associate a public key with a particular person. Once again, to prove that the person who claims it is his public key also possesses private key, that's absolutely okay, easy.
Wait, so in this case, we may need to have some authority that is legitimate to prove that some signature belongs to some person.
Absolutely right. Only that way. Either this is done by some authority, so they really check other, let's say, paper document, they check the passport, the American passport of Mr. Donald Trump. He comes to the certification center, produces his identity, and ideally then it is done that way. In the presence of this authority, he generates his public key and private key. So basically he takes a random number generator, generates two random primes, P and Q, from them produces E and N. These E and N are certified to belong to him, published somewhere by the authority. Yes, this P and N is the public key of Mr. Donald Trump. And then he walks away also carrying his P and Q, which are private components, and therefore his private key D derived from them. So that way, in a more decentralized setup, this is done by a so-called web of trust. So basically, somehow it is a whole hierarchy. I know a certain person and I'm trusted by others. So that person comes to me. I certify using my digital signature, that this is a valid public key of Mr. Trump because it happened that I'm personally acquainted with Mr. Trump. Okay? You are my students. You are probably, well, maybe will be personally acquainted with me, or some of you are, although I'm lecturing from a remote location now, and therefore you would probably trust me, and therefore you trust that, trust Mr. Trump as well, because I signed for having known Mr. Trump and that his public key really belongs to him. By the way, this doesn't mean that I signed for Mr. Trump being a good fellow and just, promoting peace in the whole world. That's what I do not sign for. I would only sign for the fact that this public key really belongs to the physical Mr. Trump. Okay? So that's how it works. And setting up this infrastructure in, I would say, in a correct way requires, I would say, serious care on the security architect side. In Linux systems, you get this infrastructure with any Linux installation for free. under the etc. etc. pk11 folder, you would have the whole web of trust and top level certification authorities, secondary certification authorities, and so on. So this is all done, I would say, by any existing Linux operating system infrastructure. Other systems like Windows, they may or may not have similar setups. We are in the open source community, so that problem is more or less managed in that case. Until then, when you install new software, for example, in your Linux system, then this web of trust may or may not be able to identify the developer of a software. And then you ask the question, actually, should you or not incorporate the corresponding public key as a trusted one, that the software you are installing is indeed from a reputable developer and would not, for example, install any harmful mechanisms on your computer. So this is a very interesting topic on its own, and if you came from the computer security background, then I have no doubt that you will see it many times in the future. Okay, so now we are going to elliptic curves finally, having done the RSA framework. So basically, one moment, something is wrong with my pen. My pen switched to something obscure. Just a second. Okay, oh my God. Sorry. Does it work or not? Yes, okay. Elliptic curves. You know, the biggest mystery about elliptic curves is why they are called elliptic. I would be very much grateful to you if you find out and tell me. Because you remember from your first year algebra, what is the equation of an ellipse? Do you remember?
X divided by A.
X squared.
X squared divided by A
squared. Y squared over B squared
is equal to 1.
Is equal to 1. So basically it is a quadratic curve. Ellipse is a quadratic curve. But somehow elliptic curves are cubics. Maybe the term elliptic curve is used because in some very peculiar fields, we have already mentioned Galois fields, and there are fields of small characteristics. So for example, characteristics 2 and 3. And then the general formula for an ellipse can involve cubics. Maybe for that reason. Maybe it is just a historical artifact. But in fact, elliptic curves are just solutions to the following equation. Y squared equals to x cubed plus ax. Please see x squared is omitted. Plus b. So these are elliptic curves. Obviously, as x tends to plus infinity, then the right-hand side sooner or later will become positive, and it is going to infinity as x cubed. And therefore, for sufficiently large values of x, there would be 2 values of y. But in general, for small x, and depending on the values of a and b, there could be quite different behaviors of these elliptic curves. In particular, there is a requirement that the discriminant of this curve, you remember obviously the discriminant of a quadratic equation, so there is discriminant of an elliptic curve as well, which is up to a factor equal to 4a cubed plus 27b squared must not be equal to 0. So the simplest elliptic curve, for example, y squared equals to x cubed, where a and b are equal to 0, is no good. Geometrically, we can see why it is no good. This means that y equals to plus minus x to the power 3 over 2, right? Which means that for x, and obviously this is only possible for x greater than or equal to 0. So we have one branch here, and we have another symmetric branch. Point 0 is called a cusp in this case. So what can we say about this point with a cusp?
Its derivative is not defined.
Well, it is defined. It is a point 0, 0. But in this point, there is no tangential line to the curve. All right? And that's precisely what we would like to avoid. So we would like our curve to be smooth, without such cusp points and without self-intersections. It is also possible to get a cubic curve which would contain some kind of self-intersection, something like this. So again, in this point, in the point of self-intersection, the tangential line to this curve is not well defined. The discriminant being non-zero guarantees that there are no cusps and there are no self-intersections. Let's have a look how typical cubic curves, elliptic curves can look like. Okay, can you see the graphs?
Yes.
Okay, so you see there are two possible cases. This curve does not even necessarily consist of one branch. It is possible that it has a closed part and then an infinite part, which again tends to infinity as x to the power 3 over 2 as x tends to plus infinity. Or, as in the second example, by the way, both of them are non-degenerate. That's okay. For both curves depicted here, the discriminant is not 0. Or in a more general situation, we have one continuous curve, as in the example, as in the second example. Okay. Now a very important notion. We will define so-called addition of points over an elliptic curve. So basically the idea is the following. Taking 2 points P and Q on the elliptic curve, and we also, it is important, apart from this curve, we also define a 0 point, so-called 0 point, which is the infinite point. Infinite point means x equals to infinity, y equals to 0. And you can think of this curve being a closed one going through the infinity point. So it, for example, it goes to, y goes to plus infinity and returns through the same infinite point from minus infinity, making a closed loop. This would be a useful notion. We can't depict this point, but we assume that it is the curve given by this equation plus the infinite point. Okay. Then suppose that there are points P and Q, and we define addition of points. So basically what we do, consider the first case, the generic one. We take P and Q, draw a straight line from P to Q, and you know what? This straight line, under any genericity conditions, would intersect the curve once again. There would be a third point R where this line intersects the curve. Whatever a pair of P and Q you construct. Well, there might be a certain situation when, like here, for example, your line PQ is tangential to the elliptic curve in point Q, right? In that case, the third intersection point coincides, is supposed to coincide with Q. So here we have PQR, all three different points. In this case, we have PQQ. The third point is the same as Q, because in the point Q, our straight line is tangential to the elliptic curve. Or it may be that our line PQ is vertical, right? Completely vertical. In that case, we say that it intersects our curve in the infinity point. And this infinity point is the same point as we identify notionally with 0, but more about that is later. So in this case, P, Q, and infinity are the three intersection points. Or we may, for example, pass a straight line through the point, leftmost point P in the curve, vertically. In this case, actually, it is not a single point P, but double points, P and P itself, because the line in this case is tangential to our curve, and therefore any tangential point counts twice. So we have P and P, and yet another intersection point is the infinity point. So basically we can say that with these extra definitions, taking the multiplicity of points into account, so any tangential point comes with multiplicity 2, we can say that any straight line intersects the elliptic curve in 3 points. And this is important because we would say by definition, and we would work out the algebra of this definition later on in the next lecture, we would say that by our definition, we say that the sum of these 3 points, P, Q, and R, for example, is notionally 0. And the infinity point stands for 0 itself. So infinity and 0 are the same thing in the arithmetic of elliptic curves. Any 3 points belonging to a straight line and belonging to our elliptic curve, counting the multiplicity of points, they are considered to have a sum 0. And therefore, we can extend this definition a little bit further, looking into the third picture here. If we say p plus q plus 0, which is the same as infinity point, is 0 according to our definition, which means that we can notionally say that q is the inverse of p. And indeed, in elliptic curve, the inverse of any point is the point reflected around the x-axis. So in this case, indeed, q is a reflection of p. So basically, what we do, I'm trying to give an informal introduction here. We are somehow defining addition of points lying on an elliptic curve. So, for example, in this case, all these 3 points, P, Q, and R, add up to 0, which is the same as to infinity in our definitions. And this means that if we take, for example, P plus Q and then reflect R against the x-axis, then we could say that R is a sum of P plus Q, because P plus Q plus minus that point would be equal to 0 according to our definition. Very abstract notation of addition, very unusual one, but that's how we define it on elliptic curves, and that's why we use actually elliptic curves. So why do you think, I will conclude this lecture by a question, okay, why do you think we are using our curves precisely of that equation, y squared equals to x cubed plus ax plus b? So why are we using it that way? Why not the 4th degree, not 5th? Why y squared here, not just y? Because if we consider a family of curves given by this equation, under the condition that the discriminant is not equal to 0, then for any 3 points lying on a curve and a straight line, let me put it that way, then any pair of points on a curve being connected on a straight line results in a third point, given the multiplicity. Or put it another way, any straight line which at all intersects our curve intersects it in 3 points, including the multiplicities. And that's important. So we look at this curve actually, and we may play with it. Try to draw a straight line in such a way that somewhere it intersects our curve, and then it wouldn't intersect it again. Okay, x line, x-axis, for example, horizontal line, has only one intersection. Well, not true. It has other intersections in the infinity point. If it now comes at a slightest angle, then you would have other intersections. This allows us to define addition of the points. This might be not so clear from the geometric point of view, but we would work it out from the algebraic point of view in the next lecture. So this cubic elliptic curve, let me put it that way, is a particular way to define addition of points by drawing straight lines between them and finding a third intersection point with the curve. Okay. I think we're done for today. Any questions, please?
Can we ask questions not about the topic, but about the course in general?
Yes.
Do you have any plans considering related to the exam?
Any plans considering the exam? How it would look like?
Yeah.
Not defined yet. I would say that we have some theoretical material here, for example, related to elliptic curves. But after that, we would have more about software architectures rather than a theory. And if our course is predominantly about software architectures, then any written exam with solving problems is typically not suitable to that. So from that point of view, I'm much more inclined into a multiple choice model exam. You have seen them, no doubt, right?
Yes.
I think it would be most appropriate in that case.
Thank you.
Okay. So we meet again on Monday, and we would put our discussion of elliptic curves, which used to be geometric so far, on an algebraic foundation. So we will see how, for example, given 2 points P and Q, we can really find the point, the third point R. Okay?
Yes.
Thank you. We're done. Thanks a lot.
Thank you.
Thanks. Bye.
Bye.